If you find that the open circuit signal has an exit point, you can continue on. If you don't find the open circuit signal after the exit point of the shield, you'll have to remove the shield and then examine the circuit closer. There could be some cases where you have to trace a wire harness, or maybe some wires removed from the vehicle's electrical system and laid out on the bench. You need to be aware that the open circuit signals will capacitive couple into neighboring floating wires. For instance, here we have a wire harness with 6 wires going through it. The switch we left open to represent a problem break in the wire that we need to find. We have isolated the circuit we want to trace, and the green signal lead is connected exclusively to it. The transmitter is now injecting an open circuit signal into our problem circuit. Now, pay close attention here. Let's turn on the smart receiver and detect the open circuit signal. Now, lock the reception sensitivity by pressing the power sensitivity lock button. As we trace the wire, we pass right over the open switch, and the open circuit signal continues to transmit along the circuit way past the break. The open circuit signal is capacitive coupling into its neighboring floating wires, and they're transmitting open circuit signals too. This condition makes it difficult to detect the break in our circuit. There are a couple of solutions to this problem. First, we can connect the neighboring floating wires to a positive voltage. If you were diagnosing the vehicle, you could solve this coupling problem pretty easily by turning the ignition key to the on position. Sometimes you can just turn the switches that go to the neighboring circuits on, and this will eliminate capacitive coupling. In this case here, I'm going to physically connect a positive voltage to all neighboring floating wires. Now let's trace the circuit again. The smart receiver now stops at the open switch. Here's a little tip. As you get close to the break in the circuit, try wiggling or flexing the wires to see if you can get it to make contact. Just like we're simulating by flipping this switch here. If it makes contact with a circuit to ground, you'll be instantly alerted by the smart transmitter's tone. This simple technique is called a wiggle test. It's important to understand that floating parallel wires that are capacitive coupling are weaker than the signal that is connected directly to the transmitter signal lead. You can easily detect the difference between a weaker and a stronger signal by observing the distance of the circuit and the smart receiver at the moment of detection. In our circuit, we're injecting the open circuit signal exclusively into the wire that's leading to the open switch. The parallel floating wires are all capacitive coupling and transmitting open circuit signals along them. As we trace them, we pass right over the open switch. Let's do something different now. Slowly, lower the receiver onto the main circuit that has the signal lead connected to it. As you can see, the receiver detects the open circuit signal about 2 inches away. Now, keep the receiver at this distance and then trace the circuit. It's here at the open switch where we lose the signal. By holding the smart receiver at a constant distance from the transmitting circuit while you're tracing is the recommended way to keep you on track, as well as knowing a weak signal from a strong signal. In this example, we've got a red wire wrapped around a yellow wire. The red wire is cut right here, and we're injecting a signal into the red wire with the transmitter's signal lead. The yellow wire is isolated from the red wire, however, it is floating, meaning it's not connected to ground or positive. And of course, as we learned earlier, it is capacitive coupling with the red wire that is transmitting the open circuit signal. The receiver uses the whole area from the tip of the wire harness probe to the bottom of the housing as a pickup for the open circuit signal. Remember to hold the distance between the receiver and the circuit as you trace it out. Here, the strong signal is being detected about 4 inches away. As you can see, by holding it about 4 inches away, as you trace the circuit, the signal stops right when you pass over the cut in the wire. I like to gauge the reception distance often so I know we're on the right circuit. So if I come across another wire that requires me to get closer than 4 inches before the signal detection, I know instantly that it's a weak signal and I need to avoid following this wire. We need to stay on the wire that detects the signal about 4 inches away. One of the best tools that I use that complements the ECT2000 in tracing open circuit signals is the Power Probe 3. It keeps me on track because it detects the open circuit signal by direct contact of its tip to the open circuit signal's lead. This is a positive indication that you're on the correct circuit. We didn't intend this video to be a training tool for the Power Probe 3, but since we're on the subject of using it for open circuit signals, we'll touch briefly on a few important details. The Power Probe 3 will detect your open circuit signal because it has an invaluable feature built into its Power Probe mode. It has the ability to pick up circuit noise or signals, and you can hear them through the speaker. At the same time, it'll give you a peak-to-peak reading on the display. Some may know this peak-to-peak term as min-max. Just for your information, the min-max reading of the transmitter's open circuit signal is about 7.2 or 7.3 volts peak-to-peak. So therefore, the Power Probe should have its voltage level threshold set at 5 volts. Now let's get back to our open circuit that's capacitive coupling. Contact the tip of the Power Probe 3 to the signal lead. Now to the red wire that is cut on this side. And now contact the other side. As you can see, this is how you can determine a direct signal from a capacitive coupled signal that is weaker. The Power Probe is also great for verifying a short circuit. Just connect it to the vehicle's battery. When you press the power switch forward, it conducts a positive battery voltage straight to the tip. This means that you can apply power to electrical components and circuits to see if they work. When you apply power to a shorted circuit with the Power Probe, it's the same as shorting out the Power Probe itself. Since the Power Probe is short circuit protected, it will trip its circuit breaker before any damage can be done to it. Here's how to verify a short circuit using the Power Probe without tripping its circuit breaker. You contact the circuit with the Power Probe's tip. The green LED shows continuity to ground. Now, quickly press and release the power button. Did you see how the LEDs flickered off at that instant? That's because you had driven a voltage into a short to ground. Let's do it one more time. This circuit shows that when the LEDs go out at the instant you press the power button, you have verified a short circuit to ground. Let's fix the short and verify it again. The polarity change of the indicators show that you're now contacting a circuit that is not shorted to ground. Thank you for taking the time to familiarize yourself with the ECT2000. Review this DVD as often as you like. For more information, go to our website at www.powerprobe.com.